Welcome to the Nanovation Podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com. Thank you to the Chi Foundation for their generous financial support.
That's a big number.
Right.
And so I like those kinds of projects. Anything I can do will be beneficial. And so decided that was something that would be worth looking at.
That's Dennis Hess from the School of Chemical and Biomolecular Engineering at Georgia Tech. He joined the podcast to talk about the early days of the semiconductor industry. We discussed the birth of Fairchild Semiconductor, the so-called traitorous 8, and their groundbreaking process innovations that still underlie integrated circuit manufacturing. There is an important take-home message in this episode. It's not usually the best-performing material that wins. Rather, like silicon, it's the material with good enough performance that is simultaneously manufacturable. This point is essential to keep in mind, as Moore's Law likely comes to an end, and the semiconductor industry looks for its next big thing. Dennis has long been a mentor of mine. He and I can often be found in the hallway chatting about any issue of the day, and I'm sure you'll see through this discussion why I've learned so much from him. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. Today, we're really lucky to have Dennis Hess. Technically, your title is Professor and Thomas C. Deloche Jr. Chair in Chemical and Biomolecular Engineering here at Georgia Tech. So welcome.
Thank you. Good to be here.
We'll get to the main topic, which is semiconductor processing and the semiconductor industry in a second, but let me give you a sense for Dennis's long and distinguished career, which after your PhD was straight to Fairchild, right?
Correct.
So Fairchild Semiconductor, who I think will play a prominent role in today's discussion. You spent some time there and then went on to be a faculty member at Berkeley.
Correct.
In California. And then after some time at Berkeley, you thought you'd go and try your hand at the chair's position at Lehigh, which is where you got your PhD.
That's correct, but in physical chemistry, not chemical engineering.
Right. Okay, so in PChem. And then after that came to Georgia Tech, and you've been here ever since.
That's correct.
Okay.
Joined here in 96. Grew up in Pennsylvania, and many of the relatives, the ones that are still with us, are still in Pennsylvania. Not too many ventured far away. It was just us rebels that went to California.
I should say that Dennis has been an informal mentor of mine for the last 8 years, and so we should thank him for that. I
learn more from the people I'm mentoring than they do from me.
Dennis is one of those mentors, and I think anyone who's listening to the podcast who thinks, I need to get myself a mentor, the answer is yes, you do. And you need to find somebody who is willing to tell you about the unknown unknowns. Someone who tells you what you don't think you need to know, because, everyone's kind of smart, but even smart people don't always know what questions to ask. And so a good mentor, in my opinion, is the kind of person who tells you those things. And Dennis has been that for me. Why don't we talk a minute about kind of the research you've done over the years? Can you give us a flavor for the types of research projects your lab has tackled?
All of the work that we've done has involved thin films in one sort or another, and usually that means films anywhere from a few nanometers up to a micron or so.
So this would be a coating on something.
So this is a coating, yes, for a variety of purposes. Initially, all centered on the semiconductor industry, because what I did at Fairchild sort of set the stage for most of what I did for the next 35 years. Simply because I worked on films and coatings and interfaces and surfaces there. And so my applications were primarily in that area. We've gotten away from that somewhat. I don't do too much in the semiconductor industry anymore. It's more in surface modification to control wetting and adhesion and mobility of liquids. But I always have a soft spot for the semiconductor industry because that's where I got started in plasmas. Plasmas were just starting to come in as I left Fairchild. So they were really implemented strongly in the industry in the late 70s and early 80s. And I got introduced to them in the early 70s and mid-70s when I was at Fairchild.
So why don't we talk about plasmas for a bit, because I don't think the average listener has any clue what that means. And when I've heard you speak about them in the past, you've argued that when you started, neither did anybody else.
No, that's right. I'm not sure I know now. These are very complicated systems, but they're essentially ionized gases, but not the type of gases that you would think of in fusion plasmas, which are equilibrium plasmas. That is, you have as many ions as you do electrons and neutral species. In these non-equilibrium plasmas that are used to process thin films, you have a non-equilibrium state where you have a very few electrons and an equal number of ions and a large number, and that means many orders of magnitude, higher concentration of neutral species. So the neutral species are responsible for most of the chemistry. The ions are responsible for modifying the surface because they impinge on the surface as a result of the surface being negatively charged and the ions striking. And so this breaks bonds and promotes reactions. The electrons are important because they're being accelerated by the radio frequency field. They collide with neutral gas phase molecules and dissociate and ionize them, so that now we overcome kinetic limitations in bond breaking by these electrons that are very high energy from a kinetic energy standpoint, but very low temperature. So the actual temperature that you'd measure would be probably less than 100 degrees centigrade. But the electron temperature, if you convert the velocity into a temperature, is 10,000 to 100,000 Kelvin.
So reactive.
So highly reactive system, and that allows you to carry out reactions at low temperatures that otherwise might take 800 to 1,000 C to have any rate whatsoever.
And this was really important in the semiconductor industry because you had impurities that you had put in the silicon, let's say, and that defined the transistor, the source, the channel, or the drain, and you didn't want them going anywhere during subsequent processing.
Correct. You also had photoresist on the surface in many cases, and you could not go to elevated temperature in order to etch that.
Right.
So if you're going to etch patterns to form devices and circuits, now you need to protect areas you do not want to etch. And if you have to go to elevated temperature to do that, photoresist doesn't hold up well.
So plasmas then are designed to accelerate chemical reactions at low temperature, which had a lot of valuable aspects in processing. Do you have some sense for how that came about? And how that was initially brought into the industry?
Yes, it didn't come about in terms of the low temperature particularly. It came about because I'm trying to remember the guy's name that originally started this, but he decided that stripping resist from a surface using nasty chemicals, which they were, and these reactive chemicals would actually start to attack some of the films and devices that you made on the circuit. So he decided if he created oxygen atoms, he could burn away this carbon, hydrogen, oxygen material. And so he started to use a plasma to do exactly that. And, of course, you couldn't use a DC plasma because you had insulators on the surface. So you just charge this thing up. And so you had to go to an RF. And so he started out stripping photoresist. That was the first application.
Interesting.
Which actually wasn't a good application because the photoresists in those days, back in the 60s and early 70s, the photoresists were pretty dirty. And they had metal ions in them, and this would end up incorporating metal ions because of the ion bombardment into the devices. And so two things had to happen. We had to learn more about the plasmas, and we had to learn more about fabricating resist materials that weren't so dirty.
Right.
But that's where it started. And then people at the two main players from that point on were HP and IBM, who decided that maybe if you used a sputtering type arrangement, maybe you could actually etch patterns, not just strip materials. And so that's where that started. Okay. And so by the time we got to the early 80s, this was a routine set of processes. You stripped resist, but you also patterned materials.
So You mentioned this briefly in passing a second ago when you said that you don't do as much work in semiconductor processing anymore. You've spent some time working on alternative materials, and one that I'm familiar with is your work on paper. I think that work is fascinating because you've been bringing a lot of processing know-how from the semiconductor industry and seeing how it can be applied with paper. Can you talk about a little bit what you've done there?
Sure. Well, this got started not in the direction we've ended up, but in a very different direction. So at that time, it was IPST, Institute for Paper Science and Technology. It's now RBI, Renewable Bioresources Institute. But one of the individuals who left some years later, perhaps because of what we did, as he encouraged us to do this, but asked me if I could develop a coating for paper that would facilitate de-inking. And when I quizzed him a little bit, I don't know anything about paper manufacture at that point. I didn't know anything about de-inking. And I asked a few questions, and what came out of it was that when paper is de-inked to recycle, you lose 20 to 25% of the fibers. Now, when you think of that in terms of tonnage, that's a big number.
Right.
And so I like those kinds of projects. Anything I can do will be beneficial. And so decided that was something that would be worth looking at.
Right.
And so how do you deposit a film on paper? Well, you can't go to elevated temperature, so plasma was the logical choice. And so we started by just depositing a fluorocarbon layer, doing a plasma-based polymerization process using some fluorine-containing precursor.
So a Teflon-like film.
Teflon-like film, yeah, except it was a little different than Teflon. Teflon has a fluorine-to-carbon ratio of 2. These films have a fluorine-to-carbon ratio of about 1.1. So they're carbon-rich. They're very tough because they were plasma deposited. They don't start to degrade until about 250 to 300 C. And so these things were very stable, and we started looking at how the surface was affected by these thin coatings. And these coatings were 100 nanometers, weren't very thick. So as we're starting to think about the recycle of his paper into de-inking and starting to do some preliminary experiments, a master's student finished up, and we took on a PhD student, Bala Balu. Bala was taking paper science courses at that point in time. He was taking my elective course on plasma science and technology, and he was listening to discussions in group meetings, and I had 2 joint students with C.P. Wong. And CP got me involved in this project because he was interested in designing superhydrophobic surfaces on glass and on silicon for packaging applications. So this student is listening to all this stuff, and he came into my office one day and said, "Can we make paper superhydrophobic?"
Water repellent.
Water repellent. And I said, "I don't know. Can you?" I said, "What have you got in mind?"
Yeah.
Well, we had just finished talking about rate differences in etching materials when they're amorphous versus crystalline or polycrystalline. He had listened to all this business that we were talking about in the group meeting about making surfaces water repellent, and he was reading in the paper science course the structure of cellulose as it's processed. And as you process cellulose, it has crystalline and amorphous regions. So his thought was maybe we can selectively remove the amorphous material, leave the crystalline behind. Those crystallites are the same size as the whiskers on the lotus leaf. Mm. And he put all this together, not bad for a second-year student, much better than his mentor. And so I said, okay, let's just give this a shot. Within 3 months, we had superhydrophobic paper.
Wow.
And we never went back to the de-inking.
So there's some great images I've seen of this where you literally have droplets of water that look like spheres sitting on top of this paper that you've processed with this plasma technique.
That's right.
I really want to get into the semiconductor industry thing, but you've taken this so much further. Now you can do super oleophobic coatings, which are extremely oil repellent. Right. In fact, I believe I've seen where you have coatings that can both repel oil and water.
That's right.
It's really beautiful interdisciplinary work. And for those wondering, I should say that in the Southeast we have a huge forestry industry because of where we are, kind of like the Northwest of the United States. And so at Georgia Tech, there's a center for renewable resources like wood and paper and things like that. And so Dennis is connected through that institute, and that's kind of how this got started. Because I think if you were somewhere else, you wouldn't necessarily have done this.
Not necessarily. No, somebody would have had to ask me to look at this, and then even then, if it hadn't been for the student who was simultaneously looking at all these different areas and just asked the right question.
Yeah.
And as usual, the thesis director has no answers, but the thesis director has more questions. And so we started looking at this, and it turned out to be very interesting to the point, I mean, we didn't invent how to make superhydrophobic surface. Nature did that, first of all.
Right.
Lots of other people have done this.
Sure.
But there are very, very few people who have attempted and succeeded in making something as heterogeneous and as inexpensive as paper into this very high value added surface.
Right.
And that's what's been the fun part of this. I usually describe this as we should not have been allowed to have this much fun.
I think most academics would agree with you, or they should agree with you, because it's quite a privilege to be able to do these kinds of things. So I know Dennis has a long experience with the semiconductor industry, as he was describing earlier. And, one of the themes on the podcast is clearly around nanotechnology. And we've had discussions about the semiconductor industry and integrated circuits in the past. And I've argued that transistors are one of the first nanotechnologies, even before people even use that word. And I actually think it's really valuable to go back and look at what got us to where we are today. So if you look at episode 4 with Eric Vogel, we talked about kind of what the present-day situation looks like. What are the challenges to current technology? But I think it's very difficult to understand those challenges and where to go next without recognizing how we got to where we are today. And so that's why I thought it'd be great to invite Dennis onto the podcast. I think this goes all the way back. We could go infinitely back, but we won't go back to the invention or the discovery of semiconductors. Let's go back to Fairchild Semiconductor. Dennis, can you talk about what they were and how they started?
So it's really an interesting story, which I only learned after I was at Fairchild for some time. Fairchild started out as Fairchild Aviation, and this was in 1927. And they were making spy cameras for Department of Defense. In 1944, they changed their name to Fairchild Camera and Instrument. And if you recognize the dates, this is World War II. Okay? And so they were making machine gun cameras, X-ray cameras, radar cameras, and all of those things. That continued through the Korean War, which ended early, I think it was 1953 or something or other like that. So most of their business was with the U.S. government. So nice profit margins with those sorts of things.
Yeah.
They decided, so after the wars were over, now the orders started to drop. And so they were looking for something to get into to make profits again. And one of the things they decided on was they ought to look at this digital computing that was starting to be a big deal in the 50s. Okay. So the way the link came up to the semiconductor industry was William Shockley was at Bell Labs, and actually two of the people in his group, Brattain and Bardeen, invented the point contact transistor in 1947. So Shockley wasn't directly involved in that. He was supervising the people, but he decided this was something that needed to be explored, and he decided to go off on his own and start his own company, and he did that in 1954. And his intent was to use diodes as the basis for the commercial applications of these electronic devices. And so he set up this company. And Shockley had a lot of problems. Okay, I'll talk about those in just a minute. All right, but one of the things he was real good at was hiring talented people. And two of the people who I'm sure most of the listeners will recognize names are Bob Noyce and Gordon Moore. And those were two of the people that he hired in his group. And he wanted them to work on these diodes. Well, Shockley's problems overrode his brilliance, unfortunately. He did some very strange things. He was very, very bad people manager. I had never met this guy, but I heard plenty of stories from people that interacted with him, and I've read a lot about him. Apparently, he changed his opinions and directions that he wanted the group to go very frequently. That frustrates everybody. He held public firings. He would get the groups together and fire someone. He asked employees to take lie detector tests.
I've heard that story.
Yeah, he refused to consider alternative views. If it wasn't his view, it was wrong, and he insisted that diodes were the way to go. So a number of the employees got fed up with this pretty quickly and decided they were going to leave. So remember, this started in 1954, and Fairchild was founded in 1957. So it didn't take very long for people to get fed up. And they decided, with Bob Noyce as sort of the instigator on this, that they would leave as a group of 8 because they liked working together. They were an extraordinarily impressive group. If you go take a look at who was in this group, they are extremely impressive. And I want to pitch a book that talks about exactly what we're talking about now, and it's called The Makers of the Microchip. This was published by MIT Press in 2010. And it covers the years at Fairchild from 1957, when Fairchild Semiconductor was founded, to 1961. That's a pretty short time frame. Over that time frame, the whole basis for Silicon Valley was developed at this place. And it's just phenomenal. I always wonder when these history books are written, okay, how much of this is fact and how much of this is sort of, well, this makes a nice story sort of information. I can't judge that fully, but the information that I got from people I worked with at Fairchild, those pieces are correct in the book. That's all I can say. And I presume from that virtually all the rest of it is as well. But this book includes pictures of notebooks, okay, so notebook entries, lab notebook entries, and memos that were sent by Noyce and Moore. And it's fascinating read, and it's an easy read, and it's pretty neat.
So I'll put a link to that in the show notes so people can get access to that.
Okay, good. So coming back to Fairchild Camera and Instrument, this was the opportunity they were looking for, and they had a go-between between Bob Noyce and venture capitalists and so on who were willing to invest in this and help them get funding from Fairchild Camera and Instrument. And so this was founded in 1957. The 8 employees that left were dubbed the Traitorous 8 by Shockley. Shockley was very unhappy about this whole thing. They were all late 20s to early 30s.
Yeah.
Just a brilliant group of people.
And diverse in terms of their background.
Oh, extremely so. So there were physicists. So Gordon Moore was a physical chemist, and Bob Noyce was a physicist, and there were double E's in there and various material science types, and mostly PhDs, but not all. There were a couple that had worked for Western Electric, which was the manufacturing arm of Bell Laboratories.
There's another piece of this that I want to mention because I think it doesn't get talked about enough in general. I think they approached something like 35 different venture capitalists or 35 some odd potential funders. Yeah. And I guess venture capital was not a term. They kind of started it. This was the beginning of it. Yep. And all of them, except for Sherman Fairchild, turned them down.
Yes. I didn't know the number. I had not heard the number before. But yes, this was not something that was an obvious connection. The group of 8 wanted to leave Shockley, and Fairchild Camera and Instrument happened to be looking for an investment in this kind of area. And the match was made, and I forget the guy's name, but it's in the book, that made this match and decided to take the shot at this and see what happened.
Yeah, and I think it's just a reminder of, you have to try many, many times in pretty much all cases. People remember the successes, but behind all successes are these kinds of stories about just perseverance and trying, in this case, that many potential funders.
One of the things that struck me, which I didn't realize before I read the book, they have a memo from Gordon Moore in 1959. Now, remember, that was started 2 years before, where Gordon changed the direction of the Fairchild Semiconductor laboratories to be one of looking at basic research. Because his concern was that these trial and error approaches weren't going to get us anywhere fast. We need to start to understand what it is that's going on, and so focus on the fundamentals of silicon technology. Even that was something special because, remember, the point contact transistor was in germanium.
Right.
And so germanium was supposed to be the material that was going to be the foreshadow of the electronics industry, if there was such a thing at that point. And this group decided silicon was the right material. And I've never seen a good explanation for that, because germanium's carrier mobility, so the speed with which you can transport electrons and holes, is about 3 times that of silicon.
Which means, in theory, it's a faster semiconductor.
In theory, it should be.
Yeah.
Yep. But you have to process it.
Right. So let's drill down into this. This is that point is really an important one, and I think people who listen to the podcast know that I've brought this up many times, that it's not just the material's properties, but it's whether you can also process something with sufficient materials properties, right? And that's kind of where silicon came in. So let's then talk about. You said Fairchild laid the foundation for the electronics industry. Can you talk about what those major breakthroughs were that started this?
Sure. I think one of the first ones was this whole idea of planar technology. So up until then, so when you get away from the point contact transistor, you go into what were called mesas. So you grew silicon and doped it as you grew it. So in order to make a transistor, you need P-type regions where holes are the primary carrier, N-type regions where electrons are the primary carrier. And you need these interfaces, these junctions between these different types of silicon or any semiconductor to make a device. So these were grown by changing the doping level as you pulled the crystal out of a melt and formed the bulk crystal. And then they were sectioned, and you made your devices. And so these were termed mesas because they were rises on the surface, and the junctions were exposed. So instabilities, moisture instability in particular, but also other contaminants, and they didn't even realize that at that point. They thought of moisture. They didn't think about other contaminants. And what Jean Herney developed was what was termed a planar transistor. And what he did was lay out diffuse junction transistors, where instead of growing a crystal with different doping levels and having junctions, he started out with a piece of silicon and selectively diffused dopants into those areas to form these PN junctions. Now you could maintain a flat surface.
And you had the junctions away from the interface.
And the junctions were buried.
The environment, right? They're buried, exactly.
Junctions were buried into the silicon. So only the very surface junction would be exposed to the atmosphere. But then Bob Noyce went one step further and said, gee, why wire up all these different devices? So you can make transistors, resistors, capacitors, diodes, and so on, and these would be connected by wires.
Right, yeah.
To make a circuit.
So let's go back here. This is... because at the time when Fairchild started, people made single transistors.
Correct.
Right? It's hard to fathom today, right? But so in that book, I think it's from the book, they talk about what Fairchild was selling these to the U.S. government for, and right,
yes.
The U.S. government was very interested in making their avionics systems faster and more lightweight and more compact. So getting away from vacuum tubes was a huge benefit. But they were selling literally single transistors. Here, I could give you one by one, and you could hold them in your hand.
That's correct.
Jack Kilby at TI was the first person to say, well, let me actually put wires between them, but literal wires, like macroscopic wires. And then this is where Gordon Moore's insight was so important. He said, that's really inefficient to literally have to hand wire
That was
these.
Noyce.
Excuse me, Noyce. Hand wire these. And we had this planar process. So continue from there as they started to integrate them, into what became the integrated circuit.
Yep. So they started integrating these directly on a piece of silicon, and this was Noyce's contribution to this. Now, Kilby did a similar thing, but in germanium and not quite in the same way. They both ended up getting credit for this big fight on patent rights for this invention, as you can well imagine. But now you got away from this instability, at least in the bulk of the material. But there was still a problem with instability at the surface. And a lot of this came down to how do we passivate or protect the surface so that it's not so susceptible to impurities and contamination and handling and all that. So the next thing that Fairchild did after this planar process, everybody and his brother, and there were lots of people in this industry because this looked like it could explode, which it subsequently did, but it looked like this was going to be a big thing. So lots of people were working on how to make controllable, reproducible transistors. And Fairchild really was the one that developed how to do this. And the person I worked for, Bruce Deal, had a major part in this because they first isolated the primary problem with the instability, and it was sodium ions.
So not water.
Not water. It was sodium ions. So it was alkali ions that were diffusing very fast in silicon dioxide, which was used as a protective layer over the surface of these planar transistors. So it's the way you protected those interfaces and surfaces to keep contaminants from getting in there. Problem is, if you think about glasses, ions like sodium diffuse pretty quickly in these, and they especially diffuse if you have a voltage across there, because now you have a field to help the driving force. So that's the main driving force at lower temperatures, to have these ions transport.
And where were the ions coming from?
So just from handling. So sodium is from your hands, just from anything. Right. If you look at any solution, if you look at any process, so these devices were processed in quartz furnace tubes. Well, you've got sodium ions in the quartz. Even though you have very pure quartz, you still have sodium ions. You were growing oxides using steam in some cases, not just oxygen. Well, water has some sodium ions in it.
If you're not careful.
If you're not, even if you are. It has some sodium ions in it, and these things get transported into these devices. So Bruce Deal told me when they first started looking at these problems and focused in on instabilities, what he always called drifts or instabilities in this silicon dioxide system. He said if you looked at the shift in voltage, and people would make capacitance voltage measurements. So they take a piece of silicon, grow an oxide and silicon dioxide layer on the top, and then put a dot of aluminum on the surface to make a capacitor. So you had aluminum, SiO2, silicon capacitor. If you scanned this in voltage and measured capacitance, you'd get a capacitance voltage plot. And where that plot appeared, where the shape took form on the voltage axis, was an indicator of what the turn-on or threshold voltage would be on a transistor. And so these were much easier to fabricate than a transistor. So everybody used CV plots to investigate this. Well, they worked with about 1,000 angstrom, so 100 nanometer oxides. Now, those were pretty thin in those days. Doesn't seem it today when there are a few nanometers, but at that time, those were pretty thin. Normally, if you have a fairly good quality oxide, the shift in voltage on that capacitance voltage plot is some fraction of a volt. Bruce told me when they first started looking at them, they'd get 100-volt shifts.
Wow.
Due to the contamination in there.
Wow.
And once they realized that and cleaned up their processing, those shifts went down to a couple volts at most.
Right.
Now you're in the order of the voltage that you're using to drive the transistor. And so just that discovery in and by itself was a huge advance.
So if we just summarize here, so first we started with these mesas with all the interfaces exposed, really a disaster. Aaron E. comes along, says we can embed most of this inside the silicon to keep those interfaces away from the environment. We knew there were still some interfaces on the top layer exposed. We tried to oxidize those. That only worked so well until Bruce Deal, and that was all before you got there?
That was all before I got there. They did all this work in the early to mid 60s. So I'd say 62.3 up to about 65.6.
Okay.
They did most of this.
So he comes along and realizes, SiO2 is great, except it's not really the SiO2 that's the problem. It's these impurity ions that are being deposited from all sorts of things. If we can control that, then we have a shot at this.
Yep. It's an interesting story. One of the places that the sodium comes from is the way we were metallizing, or we is before my time there, but the way the industry was metallizing and putting aluminum down was evaporation. So they'd go into a low-pressure system, heat up a filament where you had strands of aluminum connected to it. So as you'd heat this up, the aluminum would melt, coat the filament, and then evaporate when the temperature got high enough and coat your samples that you wanted to put aluminum structures on.
Exactly like water evaporating. So
exactly
now we're talking
like
about
water evaporating.
Metal at much higher temperatures.
Right, just have to go to higher temperatures. So they found that a lot of the sodium contamination came from these filaments. And so the industry went back to the manufacturer of these filaments and said, you need to clean this up. We can't have a sodium in there. So they said, okay, we'll develop a new process. Well, they substituted the sodium hydroxide. They substituted for sodium hydroxide etch potassium hydroxide.
So now there's potassium in everything.
No, there was potassium in there. Now, that didn't move as fast as sodium, but it was still a problem. Okay, so then they slowly got away from the evaporation and started using sputtering and things that were a little cleaner to do. But it was interesting. It shows how much was understood about the chemistry by the majority of the people who were manufacturing these devices. These were mostly physicists and double E's at the beginning. So now there's a huge contingent of chemists, chemical engineers, material scientists, and so on. But in the early days, it was a little sparse in chemical understanding.
Right. Let's talk about the patterning of the circuit. Right. So now we've embedded these different elements in the silicon, and Noyce realizes that you can connect them pretty easily. How did they do that?
So people used shadow masks, so they put masks over the surface with cutouts in them so that you could evaporate onto the surface, blank out the areas where you didn't want the metal, and just allow the metal to be evaporated through those openings. Now, that seems ridiculous in today's world when you're trying to control things to tens of nanometers. Okay, but in those days, the circuit sizes were pretty big.
Right.
Okay? So these structures, that wasn't a big deal. But pretty quickly after that, they started borrowing information from photographic industry. And the main manufacturer of what we called photoresists, so these are light-sensitive polymers, whose properties can be changed by exposure to UV and visible light so that you can selectively dissolve out regions that were either exposed or not exposed to the light using a solvent. And so Kodak was the main manufacturer of photoresists because they were used in photography, the same kinds of approaches. And that's where the structures and the approaches to defining patterns came from.
And using light versus just evaporation through, I mean, I guess it was the difficulty of, I guess I'm trying to get my mind around why photolithography and not just smaller shadow masks.
Oh, well, the smaller shadow masks, you can only get smaller to some extent because as you deposit on the shadow masks, now you build up on the sidewalls of the shadow mask. So that's one thing. So the dimension changes. But just as important as that is if you think about line of sight, so you're evaporating in a vacuum system. If you think of line of sight of these species coming from the filament, if it's not directly above the opening, now you get shadowing from the edges of the mask, and the mask has to be some thickness.
Right.
Right. And if you're making a metal mask, which is what usually used, that thickness isn't all that small.
Right.
And so you don't get very reproducible, controllable pattern sizes.
Right. And so with light, you could do that.
With light, you could do that.
Straight down, collimated light. And then you would expose this photoresist. Then you come in maybe with one of those plasma processes you were talking about earlier and remove material that was in the regions under the photoresist
that was not exposed to the photoresist. Yeah. So you define the pattern with a liquid process. So you do the exposure, and you either you either use a material that becomes more soluble upon exposure, or one that's less soluble on exposure. You can do either one, and then you dissolve out the regions that you want to remove. Now the photoresist serves as a mask, a resist, to an etching process to define a pattern in the film beneath the photoresist.
I always think of when you look at these patterns, they look a lot like those shrubbery mazes that you see, in castles in Europe and wherever.
Good analogy.
Yeah, from the top down. And when you remove what you don't want, they kind of look like that. And then you come in with this subsequent process that then goes down in those regions where the shrubbery has been removed and would effectively rip the dirt out.
That's right.
Right.
That's exactly what happens.
Yeah.
Yep. And so all that process was done with solutions. So you used liquid baths to do the etching, and the photoresist was set up so it would resist the liquids that were used as etchants for the underlying material.
Yeah.
Now we get into a problem pretty quickly as we shrunk sizes, because you had a couple issues that came up. If you used a liquid, first of all, liquid has a surface tension. So if your opening was too small and the surface tension of the liquid too high, this would simply bridge that gap and you wouldn't get etchant down into the area that you needed to etch. The second thing that was problematic as you got smaller and smaller feature sizes is that liquid etches anisotropically. It etches at the same rate in all directions. So as you etched down, you also etched laterally underneath the photoresist. That was okay when you were making 10-micron structures and your thickness was half micron. Okay, now you ended up with 9-micron structures, and that's okay. You could design for that.
Right.
But when you got to 1-micron structures, now you had a problem. You eliminated the line completely.
Yeah.
So now you needed some sort of directional etch called anisotropic etch, and that's when plasmas came in, because that allows you to do an anisotropic or directional etch as opposed to a liquid, which is always isotropic unless you have selectivity to certain crystal planes. So there are etches that you can design, but most of the materials we etch are not single crystal. Most of the materials we etch are amorphous or polycrystalline.
And even finding appropriate selectivity from different facets is hard and
not
relatively
easy.
Rare, right?
Yeah.
And so in the shrubbery maze example, it's the difference between digging that dirt out and digging out all the dirt even underneath the shrubbery versus just digging straight down only the dirt that was between the shrubbery.
Correct.
Right. So it's kind of my personal opinion that we, as a community, people who are interested in semiconductor processing, whether you're in the industry or in academia, don't think enough about these processes and how they came about and whether or not it's gospel that these are the ways you make semiconductor devices and circuits. And there's been, in my opinion, this emphasis on Moore's law, rightly, because it's this interesting observation that we can keep improving the density of devices and getting better performance at a certain rate. But to me, that kind of belies the underlying processing capability, which was this idea of deposition of materials, patterning of materials, removal of materials, this sequential process that was largely started at Fairchild that enabled all of this. And here we are today kind of running into a number of challenges with that way of doing things.
This served as the basis for the semiconductor industry from that point on, and is the reason Silicon Valley developed. I don't know if it was in the book that I referred to or if it was someplace else, but what I remember seeing is that in 1960, the planar process and the transistor were just sort of a novelty. In 1970, it was the way everything was going. Right. So 10 years, and this just exploded. Fairchild had parts in other things that they never managed to capitalize on. As far as I know, at least from what I knew about Fairchild up to the point that I got there, and from what I knew till a few years after I left, Fairchild never had a profitable metal oxide semiconductor division. And these devices are termed metal oxide semiconductor because that's the sequence that they had. They had a metal connector, they had an insulator, and a semiconductor. And they never had a profitable division, even though they developed the technology.
Right.
And that always amazed me because they had tremendous ideas. So just in the time that I was there, I learned from someone who I worked with at Fairchild and subsequently went on to Hewlett-Packard. Hewlett-Packard in about 1969 or 70 came out with the calculator, HP 35. Okay, this thing cost $350. We always joked that was the reason it was $35. So it was $350. My thesis director bought one, let me play with it for a while, and this thing could do about a dozen functions. Right. That was it. And this guy at HP told me that when he was at Fairchild, 2 years before HP came out with the calculator, Fairchild had couple of dozen calculator chips on the shelf. And the decision was made, nobody buy anything like that.
Yeah. Yeah.
Then when I was there, they developed watches, digital watches. Couldn't make them fast enough. Well, TI and a whole bunch of other places took that over, and Fairchild got out of the business within 18 months. Then they made games. Okay, so I don't know if any of the listeners. Oh yeah, I don't know if any of the listeners are old enough to remember Pong. So
I remember Pong.
This is a game that you could hook up to your TV, and it was basically like a tennis game. So there were paddles on either side of the screen, and you could move these paddles up and down, and there was a ball that would bounce in between, and you'd try to deflect it off of there. Otherwise, it would go through that end of the screen. So that was it, and everybody's fascinated with this. Well, and I played that when I was a kid, and when it got to that point, okay, after about 6 or 8 games, I had enough because there was nothing else to do with that thing. So that was it. But what Fairchild did was they came up with, they took off on this and said, all right, we're going to have something we hook up to your TV screen, but we're going to be able to play games. So they came up with race cars. They came up with blackjack. They came up with word games. And they had what they called cassettes, which plugged into this console.
Atari, at least like a predecessor to Atari.
Predecessor to Atari. And they came up with these cassettes that had 3 chips in them. I was involved in designing the process for those chips. And they were selling those things hand over foot. They could not... I had to sneak one out of they'll probably come back and sue me, but I had to sneak one out to take one home to be able to play with it because they could sell 10 times more than they could make.
Wow.
The reason you don't know about it is within 6 to 10 months they were out of the business because other companies grabbed onto this and ran with it. So Fairchild had some awfully innovative and forward-thinking ideas and implementation, but never managed to make profit out of these things.
So when did, speaking of that, when did Noyce and Moore leave Fairchild?
I think they left in '68, if I remember correctly, to form Intel. And people always wonder what Intel stands for. So it was always... intelligence, or something else. Well, they named it for integrated electronics because that was the basis of what Noyce had done and Fairchild had done up to that point in time.
Yeah, if you look at the old Intel logo, the E is lower down,
yes,
showing you it's integrated, and then electronics.
Yep.
Yeah.
Yep. So they went off and started this, and soon after that, Andy Grove joined them. So Andy Grove was at Fairchild, and he and Bruce Deal, of course, came up with the model for oxidation of silicon, so describing the rate of oxidation of silicon to grow these oxides that were instrumental in this. So they proceeded in understanding these drifts or instabilities in the silicon dioxide silicon system, and came up with a whole lot of these. Bruce used to joke that he had a talk that he put together on the 17 drifts of silicon technology. And I knew most of these, and there were 1 or 2, and Bruce would never tell me what they were. And I found out eventually that Drift 13 was when Andy Grove drifted to Intel. So Bruce had quite the sense of humor.
Yeah.
And so, but they defined these different instabilities, and some were just broken bonds in the oxide. Some were interfacial effects where you transitioned from single crystal silicon into an amorphous silicon dioxide layer. So if you think about the bonding structure at that interface, that's got to be jumbled. Okay, that's got to be a problem because you're not going to adequately bond all those bonds and not have sites where you can trap electrons or holes. And so they had to figure out how to make that interface as perfect as they could so that they could make sensitive electronic devices. And it's phenomenal what they accomplished in less than a decade.
So that work, I guess the Deal Grove model. When was that? That was at Fairchild, or
that
Intel?
was at Fairchild. No, that was at Fairchild. That was 1964. The paper was published in Journal of Applied Physics.
Okay,
and that's one of the most cited papers ever published.
This is one thing I like to tell my students, and it's one of the. It's also kind of a theme that runs through that musical Hamilton. Is that you don't really know when you publish something whether it's going to be useful in the long term, right? You really don't. I mean, so I remember when I was a postdoc, and Gerhard Ertl won the Nobel Prize for understanding the fundamental mechanism of the Haber-Bosch process, the way we make ammonia. And he'd done a bunch of beautiful surface science experiments to understand that, and a lot of people did. He was the one who won the award. You look at his top 20 most cited papers, not a single one is in any what we would call today high-impact publication. Yet all of them have thousands and thousands of references. And so I think it's important in science to do the best work you can, do what you think is valuable, and then just set it off into the world, and just know that you have very little control over what comes next.
And things cycle.
That's true,
so
too.
Things that were important for a little while and then not so important sometimes come back. So the journal that I edit, I get monthly reports on the most downloaded articles from the journal. And about a year ago, I started seeing one that was at the top of the list in downloads. And this was done by a guy that's a little bit older than me and was published in the early 1970s. We knew each other from conferences and hadn't seen that cited forever. Well, because of the turn that the processing took, all of a sudden that particular process became important again. And now it's got lots of downloads and citations again. It hadn't been cited hardly at all for 25 years.
Right. So can you talk a bit about what originally drew you to the semiconductor industry? Because you went from Lehigh out to Fairchild at a time where I think very few chemical engineers, I guess you weren't trained in chemical engineering, but still very few people had an understanding of what it was and what you would do. So what was it that led you out there?
So outside of physicists and double E's, there weren't a lot of other people in the semiconductor industry because this was an electronics industry, and chemists and chemies really don't know much about electronics. And so I got into it because I was I had been finishing my master's degree in infrared spectroscopy at Lehigh, and had decided that I wasn't going to continue for a PhD in that area, and so I was looking for a thesis project. Fred Folks had joined the faculty as department chair about a year before I finished my master's degree, and he had just come from Sprague Electric as research director. And he had a group of about 50 PhDs that were reporting to him, and they were hot into the semiconductor area at that point. So this was late 60s. And Fred was looking to get a group started, and I went to talk to him about what projects he had available. And he talked to me about two projects. One was polywater, and I don't know who you look puzzled. You've never heard of polywater. So you've never heard of polywater.
No.
Okay. So polywater was something that was coined because Boris Deryagan, who was a physical chemist in the Soviet Union, published a paper where he discovered, and I put that in quotes, I'll come back to that, discovered that water could become very viscous and basically gel under certain conditions. And then they measured the properties of water. Viscosity was orders of magnitude higher than water. And this was almost a gel-like substance. And so other people tried to reproduce what he did, and some of them managed to do exactly that. So there were all sorts of articles published about keep this away from lakes and oceans and so on, and theoreticians described in great detail how this can happen and what all this was about and so on. And it was unknown exactly what the mechanism was. So that was in the mid to late 60s. And so Fred got interested in this because he knew Deryagin personally. When he visited the Soviet Union, he stayed at Deryagin's house. And people will know Deryagin's name from colloids and interface science and so on, where he has some theories that are well known. And so Fred described this project to me, and his comment was, this is the sort of project where a young person could really make a name for himself or have no thesis at all. And I decided to go with the second project. And the second project was an outgrowth of what Fred was doing and supervising at Sprague Electric, and that was understanding a silicon dioxide system. And it was Fred's thought that the charges, these instabilities that Bruce was talking about, at the interface between silicon and silicon dioxide were oxygen vacancies. Well, that makes sense if you think of the concentration right at the silicon surface relative to SiO2. So there's got to be a transition layer between SiO2 and silicon.
Right.
And
so oxygen poor near the silicon region.
Oxygen poor. And so in solid-state physics terms, you think about oxygen vacancies. And so Fred took that tact and wanted somebody to work on growing oxides in low concentrations of oxygen. And so that's how I got introduced at first to the semiconductor industry. I was a Pennsylvania boy through and through, and so I wasn't heading out to this wild place in California. There was just there were heathens out there. Were just more than we could take. And so we had decided, my wife and I decided, we weren't going to do that. Well, I went to a conference to give a talk on my thesis work. And after I gave the talk, there was one or two talks past that, and then the session ended. Before I left the session, Bruce Deal walked up to me, and of course I had never met him before, but I knew all about his work and had about 20 references in my thesis to his work. Bruce came up and started asking me a few questions, and we chatted a little bit, and then he asked me if I had plans for dinner. I was a graduate student. Of course, I don't have plans for dinner. And so he took me to dinner, and we talked for a couple hours, and then he said, I'd like to get you out to Fairchild to interview for a position, because he said I'm starting up a new group, and he said I have a position I think you'll be interested in. And so I still didn't think any of this would happen, but I went on the interview. I'd never been to California, so I took the trip out to California and interviewed, and was very impressed with the sort of thing that they were trying to do at that point in time.
Yeah.
And so convinced my wife reluctantly that we should move to California, which we did, and took the job. But that's how I got into this, and it's all it's the old nothing beats dumb luck.
No, that's for sure. I'm chuckling also because convincing my wife to move from California to Atlanta sounds like we had similar conversations.
Understand that issue?
Yeah, right, exactly. So talk about the group a bit. Talk about what it was like to work in Bruce Deal's group.
I still miss that group, and I've been gone for a long time, and I still miss that group. We had so Bruce was a physical chemist. He hired me, and I was the newbie in the group. Okay, I was the only one who didn't know anything there. Then there was another physical chemist. There was a double E, a physicist, and a material scientist, all PhDs, varied amounts of experience in the industry and in other industries. Bruce started his career in corrosion area. And so did my thesis director. So there were all kinds of different people represented in Bruce's group. It was fantastic. We made short shrift of problems usually, because when there was something we needed to solve, if it was really a tough one, we'd lock ourselves in a room for an hour and beat on each other and argue with each other and get upset with each other about how to view this. When we came out of there, we had 2 or 3 really viable approaches, and we usually had it figured out by that time. And I've never been part of anything quite like that since. And it's not that I haven't had good collaborations. I have. Right. That was just unique. Yeah. And so much fun to be part of that. So what we were supposed to do, the position that I took over, or I should say started, because this was new. Bruce was formulating this thing, was to work with a group of people who were going to take a process and put it into production. And so Bruce and I and other members of his group would work with those individuals to develop the process, help them transfer it into production, and then pick up the next project.
It sounds a little bit. I worked at Intel for a while as a student, as a co-op student, and they have PTD. I'm not actually, to be honest, I think PTD still exists, which is Portland Technology Development, where a lot of the same things happen, and then they translate it to the main fabs.
Yep.
Yeah.
And that's what we were to do, and that's what attracted me. That I had no intention of going to the West Coast, but that opportunity and to work with someone like Bruce was more than I could turn down.
Sure.
And it was just a whole lot of fun, because the first project was controlling charges, controlling instabilities in very thick oxides. And when I say very thick oxides, these were 2-micron thick oxide layers. And we were doing a state-of-the-art process. So in 1973, when I joined, this was isoplanar silicon gate. So up to about a year or so before, it was all metal gates, all aluminum gates. Now this went to polycrystalline silicon that was doped heavily to serve as a conductor and was much easier to process, and you could process at higher temperatures. Once you put aluminum on the surface, you were limited to maybe 450 to 500 or so degrees, because melting point is about 600, 630, something like that for aluminum. So
it was mostly a processing motivation for going from metal gates to polysilicon?
Well, a couple of reasons.
Okay.
One was processing. The other was now you could control by doping level the electronic properties of the silicon.
Right.
Okay. So this allowed you some flexibility, again, to design a device to give to have certain properties.
Got it.
So the other thing that we were working on, and related to this and related to what I did for my thesis work, which is what I think got Bruce interested, the way you isolated devices. So when you put a number of different devices on a chip, you had to isolate them electrically. And the way this was done was to grow a thick oxide and then etch through the oxide down to the silicon and now build your devices. Well, this created problems in a lot of respects. And it created problems because you had this thick oxide and you were going to run interconnects, the aluminum or polysilicon or whatever, over those steps.
Right.
Now you've got a film that's less than a micron thick and it's got to go over a 2-micron step.
Right.
Not good. And lots of cracks, lots of instabilities, lots of reliability problems. So someone in the Netherlands came up with a process that they called isoplanar oxidation. And what they did was they started out with a silicon surface, grew a thin oxide on the surface, and then deposited a silicon nitride layer. Mm-hmm. Then they etched a pattern and opened up windows down to the silicon. They put this material into a furnace at 1100 centigrade in steam and oxidized for 16 hours.
Oh, wow.
This gave about a 2.2 micron thick silicon dioxide layer. But because you grew the oxide, this wasn't a deposited oxide, right. It wasn't an oxide grown across the wafer surface. Since you only grew the oxide in the silicon that was exposed, and the oxidation rate was such that when you grew an oxide of 1 micron, you used up 0.45 microns of silicon. So now you had the oxide partly buried.
Right.
Now the step height was half.
Yeah. Did people remove the steps from above the top of the silicon layer, or they just left them there and it was okay that it was half as what it used to be?
No, that's where they built the transistors. So they built the transistors in those regions that were not oxidized. That's where the transistors
that were not
went.
Oxidized, right? But
the
regions that were oxidized that had raised up because of the oxidation, so it goes down into the silicon and there's a bit above what used to be the top
about half
layer.
and half.
Half and half. And then they take off some of that layer on the top, just left it.
I mean, some of it got taken off when they cleaned because they used HF. And that's why you started out with 2.2 microns to end up with 2 microns.
Got it.
So the cleaning techniques took care of that.
Okay.
So you thinned it a little bit, but not too much. Then you could run your interconnects over that oxide, and it wasn't a high step.
Right.
And but the problem was they couldn't control the oxide charges at the bottom of these thick oxides. And so they got a bunch of instability and leakage currents and all sorts of things flowing. So my first job was to figure out how to take care of that.
Okay.
And I used what I learned in my thesis work to say, okay, we need to supply some oxygen. We need some ways to do that. And we put in a longer than it should have been, but it was adequate, annealing cycle in just a small amount of oxygen. And we fixed that problem.
That ended after the growth of the oxide?
After the growth of the oxide. Okay. And we did an anneal cycle.
Interesting.
To control those charges. So that was the first project that I worked on.
They let you keep your job.
And they let me keep my job. The second project was just as interesting, and I don't even remember the others. These two stand out. The other one was to protect the circuit upon packaging. So you take this device and you need to put it in a package because it's going to go on a printed circuit board or someplace. Mm-hmm. And so you need to protect the surface both from the packaging process and from subsequent use. And you'd like to protect it using a plastic package. It was much cheaper than a ceramic. So government issue, you did ceramic packaging because the price wasn't an issue.
Yeah.
Commercial sorts of things, you wanted to use a much cheaper package. And so plastic, of course, is permeable to moisture and other things. And so what you wanted was a good protective layer that you could put over the finished circuit. So a likely candidate for this was silicon nitride. Pretty dense, good material. Well, we grew or deposited silicon nitride in a CVD, chemical vapor deposition process. But to get any rate at all, you had to be at least at 750 centigrade.
Hot.
Usually these things were grown 8 to 850 to get any reasonable deposition rate.
Yeah.
You couldn't really thermally grow them because it was a good passivating layer. That's why you could use it as a protective layer when you did the silicon oxidation for those thick oxides.
Yeah.
That didn't oxidize.
And this
fully.
was with what, silane and ammonia?
So this was usually with a dichlorosilane at that point.
And ammonia.
And ammonia.
All right.
Yeah. And so you could deposit this silicon nitride film on the surface. But that isn't feasible with a finished circuit. And so we started looking at plasmas again. That's where I got introduced to plasmas.
I see.
So we weren't set up. I mean, there were very few systems available at that point. Applied Materials was developing these systems, and they had contacted us to see if we were interested. Well, Bruce put me on that project, so I worked with Applied Materials and evaluated and did a whole lot of tests on these nitrides that they were growing, these plasma-deposited nitrides that they could grow at anywhere from 250 to 400 degrees centigrade and get pretty decent properties. Weren't the same as a CVD, but not bad, good enough for a protective coating.
Right.
And I did about 8 or 9 months worth of work on that project, and they wouldn't let me publish it because it was proprietary.
Yeah, I can imagine.
To Fairchild, and we were locked up with non-disclosure agreements with Applied Materials and all that, and so I couldn't publish it. Bell Labs subsequently came out and published it. They did exactly what we did, and I could follow their publication according to my reports internally. The really neat part, and I still have this, I don't have many mementos left from Fairchild anymore, but we issued these internal reports as we finished these projects. It was sort of a basis for keeping our jobs in R&D, because it's mostly manufacturing. And so we issued these reports. So I got a mail envelope one day, internal, and it was a copy of the first page of this pretty long report. This was probably 40, 50 typed pages report with all kinds of graphs and data and so on. And I got a copy of this, and written across the top is, "This is really nice. This will have enormous impact on the company." It was signed Wilf Corrigan, who was the president of Fairchild at that point.
Very nice.
I kept that.
I would frame that.
That was that's a lesson, I think, for leaders, that very little needs to be done to make people feel good.
Yeah, that's for sure.
Very little.
That's
that took about 30 seconds for him to scribble that out and send it to me.
Well, so in both these projects, when I co-opted Intel, it was a bit of a different isolation. It was, I think at the time it was called deep trench isolation.
Yes.
Whereas these things got tighter and tighter together. You had to do more work to get the isolation. You kind of dig a hole first, then oxidize the hole. But pretty analogous to what you worked on.
Yep.
And the same thing with a nitride. The final step, I'm not sure if it's still that way today, but you're done with all your metal interconnects that connect the transistors, and you put down a big, thick nitride layer.
Yep.
So let's wrap up and talk about what we think is going to happen next, or where we're going to go. And we have kind of what the industry acknowledges is the end of Moore's law, right? The ITRS roadmap is effectively
disbanded.
Over. Yeah, exactly. I just bought a new computer this year. My previous one was 5 years old, and to be honest, there's not that much of an improvement in processing capability. I mean, it's more energy efficient. The screen is better, blah, 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 but it's still about the same speed as the other one. So what are we going to do?
If my crystal ball was that good,
we wouldn't be right here.
That's right.
Right now.
That's right. I'd be off somewhere,
Jamaica.
Right, enjoying myself even more than here. So, I think what's going to have to happen is we're going to go back to where the industry started, with the double E's and perhaps physicists designing new types of devices. Because one of the reasons that we run out of gas in the way we've been doing things is because as you pack devices closer and closer and closer, there's a limit to that. There's a fundamental materials limit as to how close you can pack them. And a lot of that has to do with the isolation between devices. And so when these so-called depletion regions, where you're depleted of electrons or holes between two devices overlap, that's called a short.
Right.
And so now you don't have devices that can operate in tandem. Everything's shorted out. And so now you have to come up with a different type of device. And I'm certainly not knowledgeable enough in the design of circuits and devices to know what should come next. But I think there's some things that the process people and the chemists and material scientists and so on can contribute to. And one of them that's been a huge problem for a long time, and we still don't know how to solve it fully, is heat dissipation.
Yeah.
So when you have all these devices on a chip, I mean, if you don't have even decent heat transfer, these things will glow red. Yeah. And I've seen that already.
Yeah.
These things will just, there's so much heat. There's many watts of dissipation in this little chip that's a half an inch or an inch on a side. And this thing just dissipates heat like crazy.
Most of it comes from the interconnects, too. So there's heat loss with every switching event that a transistor does, and there's definitely resistive heat loss from just passing current through the metal wires.
Oh, yeah. It's why you could make an incandescent light bulb, right?
Right, exactly.
So you get a lot of heat from that. And in fact, if there was any material other than silicon, I don't think we would have gotten nearly this far. If you've never looked at the thermal properties of silicon, look at the heat transfer ability of silicon. Thermal conductivity is within a factor of about 3 or 4 of aluminum.
Yeah.
It's amazingly conductive, and that's what saved us up to this point. But somehow we've got to figure out how to get that heat out of there or redesign the circuits. And there's a lot of interest, and has been for a number of years now, in three-dimensional circuits. So the planar process is one thing, so that's two-dimensional. But now we stack these things on top of each other. Well, that's great in one respect, in fact, in probably several respects. But in the respect of getting rid of heat,
it's worse.
It's worse. And so now we compound the issue.
Yeah.
So we need to think about not only how to design the devices and the circuits, but how to get rid of the heat. Now, the other issue is silicon, as I said, runs out of gas because of inherent material properties. So that suggests we need to go to another material.
Yeah.
Well, there have been lots and lots of saviors in material posted over the years. And the first one, of course, was gallium arsenide. And I remember a conference that I was at back, this must have been in the early to mid-'80s, there were just millions and millions and millions of dollars being sunk into development of gallium arsenide circuits. And I was at a conference where they had, and I don't remember who the plenary speaker was, but it was one of the gurus in gallium arsenide technology. And this person was one everybody looked to tell you what you should do next. All right. So he went through about 30 minutes of background and insight into gallium arsenide. And at the end, his final summary, he said, "There is absolutely no doubt that gallium arsenide is the material of the future." and it always will be.
There you go. That's right.
And it was starting to be recognized at that point that gallium arsenide had some very useful properties. Okay, so being a direct band gap material was very different than silicon and had definite advantages. But to make circuits out of this thing that would compete with silicon, so the battle cry was always they're going to replace silicon. Well, that hasn't happened yet, and I don't think it'll ever happen. You replace it for certain applications where you need particularly high speed. Even there, silicon has done pretty well in coming up with very high-speed devices just by being clever in design and processing and so on. But there's no denying that a lot of materials have electron and hole mobilities many orders of magnitude above silicon. Silicon isn't very good, and that's why germanium was looked at in the first place.
And there's plenty that are better than germanium.
That's right. That's right. And so now the big cry is 2D materials. All right. So they're interesting, lots of neat stuff going on there. Will that replace silicon? Very unlikely in my book, simply for a couple of reasons. The first one being you don't need a device that operates at warp speed for your toaster, all right, for your automobile, even for your laptop. You don't need that. Silicon, we know how to manufacture cheaply, reliably. Okay, it's going to be a long time before we can do that with any other material. Secondly, the 2D materials, except for graphene, are binary or maybe ternary. That's one of the problems that was always found with gallium arsenide or indium antimonide or any of those, is you have two materials that are very different in lots of properties, including vapor pressure.
Two atoms that comprise the material.
Atoms that comprise the binary or ternary. The properties of those atoms are very different. So if you think about volatilization, that was part of the problem with gallium arsenide. You processed it and heated it up. Well, the arsenic evaporated very easily. The gallium didn't go anywhere.
Pools up on the surface.
Right.
Yeah.
And so this is a problem. Secondly, how do you develop the interfaces? Because you're not going to build a device with a material. So you've got to have insulators on there. You've got to have conductors on there. You've got to have these interfaces and junctions. How do you make those perfect enough to have these small devices function efficiently and effectively? Well, the thousands of publications that have resulted in this from the silicon dioxide system, we know how to do that. I'm wondering whether that's not an altogether unique system, because maybe if you put enough effort into these other things, maybe you can figure it out. But that's a extraordinarily unique system, and I don't have time to go into all the uniqueness of that system. But it has been a workhorse. And so when you start looking at these other materials, they're fascinating. From a science standpoint, they're just as intriguing as can be. From a standpoint of doing anything to replace silicon in any way for normal devices, hard to imagine.
Yeah.
Now, will they develop their own niche? I expect so, just like gallium arsenide did. Okay, so there's very good use of those kinds of materials, but they're not your traditional integrated circuits that's used in basically everything. They will be specialty applications that are expensive, but the product is something you can't do any other way.
Yeah.
So that's my sort of ballpark guess as to how these things will develop.
Yeah, I agree with you in many respects. The one thing I think about, though, is we go forward into a world with new kinds of applications that do require higher computational performance.
Oh, absolutely.
Whether it's AI or something like that.
Absolutely.
You know, that is where I'm not as convinced that the way we do silicon technology is going to be able to meet those needs.
No, I agree completely. And that's what's going to drive these new materials when the performance is not of the silicon-based devices is not what you need.
Right.
So as you develop these other things, when something comes up that, okay, now all of a sudden I need this, what I mean by what I said was for the standard whatever we use in large scale at this point, there has to be a completely new application, a completely new direction that requires these very high-speed materials, and it will be, at least initially, small scale. Now, it may develop from that, but it's going to be awfully hard to compete with the cost. So if you can use silicon, you'll use it.
Yeah.
Okay? So it will only be what you're referring to is maybe in AI type application. Maybe something will come up where I need a chip that will do whatever, and silicon just isn't appropriate for it. And that's where things like gallium arsenide have come in.
Right, or 2D materials might be
2D materials. And I think there will certainly be uses for these things.
Right.
People always like to talk about replacing silicon, and that's what I was referring to.
Right.
You're not going to replace silicon, certainly not in my and probably your lifetime.
Right. It reminds me
going to happen.
a bit of, I feel like I can draw an analogy to the incandescent light bulb. Right. There it was low cost enough, worked just fine enough for most applications. And it wasn't, if you had a specialty lighting need or whatever, you'd get an LED or maybe a laser or something like that. But the incandescent light bulb worked really well for a long time.
Yep.
Dennis, thank you so much. This has really been fantastic.
Thank you. I've enjoyed it very much.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at philolab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology Building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.